Welcome back to Chapter 3. These last couple sections are going to be about scatter plots and lines of best fit. So in this section, we're going to introduce it, we're going to get some vocabulary on it, and we're going to see how we can calculate some lines of best fit. And then in the next section, we will take a look at how we can do it using more technology and get some more accurate results. So our learning targets for today is you can use a scatter plot to describe the relationship between two sets of data. So the very first question is, what is a scatter plot? A scatter plot, you just plot the points that you see. You have a bunch of points, X and Y. Now they might not be called X and Y necessarily. It might be the screen size and the cost. You have to pick which one's X, which one's Y. A lot of times, the very first one will be X, the second one will be Y, or the one that we're using to explain the other one is X. So right now, we're using the screen size to explain the cost of the TVs. And then the points are just plotted. So we have 40 comma 300. So we have 40 comma 300. We have 42 comma 350. So 42 350. So again, the point is just like plotting any kind of points that we've been doing for the past couple chapters. A couple things to notice here. The x-axis is broken. It does not start at 0. That's okay. A lot of times the x-axis won't necessarily start at 0, especially if we're dealing with something like time, like years, because when x equals 0 does not necessarily have any meaning in the problem. Like a screen size of 0 inches, well, that's not even a TV. Like that's a nothing. So having a 0-inch screen wouldn't make sense. Working with time, the year 0 probably doesn't apply to whatever situation we're looking at, unless we're looking at something on a really long-term scale. So having an x-axis that is broken is not a problem. Having a y-axis that is broken, it depends on what we're dealing with. Here, since we're dealing with cost, it's probably a good thing to start out at 0 so we get more of a true relationship. If we started at about 300, it would look like the points would be going up a lot quicker than they're actually going up. So you just have to be careful about breaking the axes because it could turn into a misleading graph, but it might not, and so you might be able to do it. It is entirely situational. So that's what scatter plots are. Now, I have some pro tips for you because these are the same pro tips that I'm telling you guys as Algebra 1 students. It's the same stuff I tell my AP Statistics students. And these tips come from, one, my experience of doing these problems, and also the experience of watching a lot of other students over many, many years do these same types of problems and the struggles that they have and ways to avoid that struggle. Now, with that being said, these tips are for specifically while doing stuff on paper. I know that right now we're doing a lot of stuff online, and so these won't necessarily be hugely applicable, but even when you're doing something online, having the paper to work at it on paper, because online you put your answers. You're not necessarily just going to jump from the problem to the answer. You're going to have to show some work. And so this applies there as well. So, some pro tips. First, use graph paper. Graph paper is going to make your graphs way more accurate. And the accuracy of your scatter plots, when we're going to be drawing trend lines or lines of best fit, which is coming up later on in just a couple minutes, we're going to be drawing those. If you are using graph paper, and all of the lines are vertical and horizontal and you can more accurately graph things, your trend line is going to be more accurate, which means anything you do with your trend line is going to be more accurate. So use graph paper. Tip number 2, use a ruler. When you're making your trend line, a ruler can be very, very helpful. Again, because we're looking at the graph to answer questions, that is an important piece. You see why these aren't particularly applicable when you're doing something on the computer. Like, you're not going to use a ruler on the computer unless it's a um, a tool for you to use in the program. The third one, use graph paper. I can't emphasize this enough. This is the single largest struggle that people have because they try to just kind of half do their graphs and they're sloppy and small, and then everything else just falls apart from there. Use graph paper. And the fourth pro tip, use graph paper. Again, I cannot emphasize it enough. Um, it is huge. It is largely or very often the biggest distinction between success and failure on this type of topic. If you do not have graph paper, let me know. I will work on a way to try to get you some graph paper. Um, it's that easy. So, looking at these scatter plots now. When we're looking at scatter plots, we're going to be looking for their association and also their correlation. I'll get to correlation in just a minute, but first we're going to look at association. So we have 3 different types of association that graphs can have. These are the 3. So we have this first one. Notice the temperature is generally increasing over time. As the x value gets bigger, the y value gets bigger. If we were to draw a trend line here, like it would be going somewhere like that, notice it has a positive slope. This is a positive association. So when one goes up, the other goes up, a positive slope, it's a positive association. The second one, as one goes up, the other one's going down. It's decreasing over time. If we were to draw a trend line, it would have a negative slope. That's a negative association. And then this last one, it doesn't really go either up or down. It's just kind of there. Sometimes we might get things that go up and then come back down. They falls in the same category, and this is just no association. It doesn't go either up or go down. Now, to tell the association when you're looking at a scatter plot, it's by observation. It doesn't take much time. You should be able to look at the graph and be like, oh, that's going up. That's a positive association. Oh, that one's going down. That's a negative association. Sometimes the no associations you have to look at just a little bit to see like, well, is it going up? Is it going down? If you really have to look that hard, it's probably no association, especially at this point. If you're looking at a table of values, you could make it into a scatter plot first, but you can also just look at the numbers. As x is getting bigger, what's y doing? Is it getting bigger? Is it getting smaller? Or is it just kind of jumping around? That would be positive, negative, and no association. So I don't have a place for you to pause this because I think by the time you hit the pause button, you'd probably have the answer. But here are 2 more graphs. So what are the associations of these? Positive, negative, or none? Give you just a second. All right, so this first one, see, that's really as much time as you really needed. In fact, by the time I finished asking the question, you very well may have had your answers already. This first one, Hey, look at that. It's going up. This is a positive association. The second one, is it going up? No. Is it going down? No. This would be no association because it's neither going up nor down. It's just kind of all over the place. And so finding association correlations that easy. Like there's no work to it. It's by observation. You look at it, it's going up, it's going down. What is it? Now, there is a way to get a more specific answer than that. We can actually measure the association with a number, and that number is called the correlation or the correlation coefficient. We'll get to that in the next section. But right now, we're going to define the correlation. And the correlation is basically the same as the association. It just means that it also has a linear relationship. Like all of this one, and this one have a linear relationship. Like we could model it with a line. Now, I'm not saying that my line that I drew is a great line to model these things, but they're all kind of linear. So when it has a linear association, that is also called a correlation. So like this one, which is this same graph as up here, it's just the line is better. It's positive, it's linear, and so this would have instead of just a positive association, this could have a positive correlation. Where are my letters? You know how sometimes you get like a part of your paper that doesn't write, like you can't write on it for whatever reason, like maybe it was erased, maybe you had some spill on it. Apparently I just found a spot on my computer monitor that I can't write on. Maybe that'll change on the next slide. So that's a positive correlation. We can also have a negative correlation, and no correlation is kind of the same thing as no association. It just means there's no linear relationship. So example like this one, there's a relationship there. Like we could actually connect those points into it's called a parabola, which is like an x squared type equation, but it's not a linear relationship, so there's no correlation there. So again, correlation and association are basically the same idea. It's just correlation also means that it's linear. So now we get to trend lines. So we graph the scatter plot. We make that line of best fit, say like that. Now, this is the line of best fit that we have here. If you were looking at, like if you did this on your paper and you made a line of best fit and your friend did the same, they made the scatter plot and they drew a line of best fit on their paper, do you think that line of best fit is going to be exactly the same? Yeah, probably not. In fact, if you had the exact same data points and you made a scatter plot twice and drew a line of best fit twice, chances are your lines of best fit aren't even going to be exactly the same. So when we're doing this by hand, there is a lot of variation. I'm not going to say error involved. There's a lot of variation because everyone's lines of best fit are going to be just a little bit different. In the next section, we'll see how to make it so they're a lot more consistent, because it's nice to be able to get a consistent model no matter who's doing it. But here we have our line of best fit. We pick 2 points that look like it's on the line. Now notice this line of best fit doesn't actually touch any of the data points. That's okay. It's modeling the data points. It should make it so that about half are above it, half are below it. And it's modeling the data. But we pick 2 points that are on the line. We have the points 2, 50 and 16, 500. If we have 2 points, we can find the equation for a line. We were doing this all last chapter. It's kind of the same thing we were doing with arithmetic sequences even. So we're going to find the equation for the line. We need a point and a slope. We have 2 points to choose from. Now we just need a slope. So our slope is going to be y minus y over x minus x. So 500 minus 50 over 16 minus 2. So that gives us 450 over 14. And 450 over 14, we could start reducing it. If we divide, it's like 32.14. So let's reduce it. We can divide both of these by 2 to get 225 over 7. And again, it is possible you could just go straight for a decimal as well. If you do, I'd round it to say 32.1. Like, you don't need too many decimal places because, I mean, our line itself was an estimate. The points on the line are still kind of estimates. We're getting points that like cross at nice places. Like this one here looks like it's 2 comma 50. It might be 1.9 comma 50. Like, it's tough to tell. So rounding it, I mean, even rounding it to 32 might be okay. I'm going to stick with 1 decimal point. So we have our slope. We have a point. I'm going to use the 2 comma 50 point. And let's make the equation for the line. So that'll be y minus the y part of the point, 50, equals our slope, 32.1, times x minus the x part of the point, which is 2. Let's put it into slope-intercept form. So we're going to distribute that 32.1. So we have y minus 50 equals 32.1x minus 64.2, because we have to distribute that. And then let's add the 50. Add the 50, so we get y equals 32.1x. The negative 64.2 plus 50 will be minus 14.2. So that is our equation. Now, a couple things we want to do, like, does the slope make sense? Because a slope is somewhere where people make mistakes. First of all, it's positive. The line's going up, so it should be positive. Does the y-intercept make sense? Looking at the graph, it's like, yeah, it looks like it hits right there and it would go a little bit negative. Now, when we look at the real world application of this, in the years starting in 2000, so that means in the year 2000, we sold negative 14.2 thousands electric hybrid cars. Like, did we actually sell negative hybrid cars? No, it would have probably been to 0. It wouldn't have gone to the negatives. So that y-intercept doesn't make sense logically, but for the model, it still makes sense. The slope, if we want to interpret the slope, that's the increase in the number of y, in this case, 1,000 electric hybrid cars sold every year. So every year we sell 32.1 thousand more hybrid electric hybrid cars. And so we can look at the slope. That's the change. How much did y increase for every change in x? Now, when you are interpreting the slope, including units is very important. And it's the number of y per whatever one of x is. And so again, in this case, number of cars sold per year. That's what we're increasing. By including units, it is way easier to make it in context, which is generally what they're looking for, because this isn't just random numbers. Like, this this is data, which is just numbers with meaning. So we want to keep that. Now, one of the things you could be doing with this is it could be asking you to make predictions. For instance, how many cars were sold in 2010? And so the year starting in 2000, so this would just be x equals 10. We would just plug that in. So y equals 32.1 times 10 minus 14.2. So 32.1 times 10 is going to be 321 minus 14.2. Then 321 minus 14 would be 307 minus the extra 0.2 is going to be 306.8. So in 2010, it predicts we sold 306.8 electric cars, which if we look at when y equals 10, we get right up here. Well, this was 300,000, so it's just above that. So that makes sense based on the graph. Now, another thing that they like to do is how about in 2020? I found another spot that my pen won't work. There we go. How about in 2020? Well, we're going to use x equals 20 here. So y equals 32.1 times 20 minus 14.2. So y equals 642 minus 14.2. 642 minus 14 would be 628 minus the extra 0.2 would be 627.8 thousand cars predicted to be sold in 2020. Now, making predictions is something that we like to do with trend lines. It's a human nature type thing. We want to have a prediction of the future, but we have to be careful. If we go too far, like if I was going to look for 2050, like, is it going to stay linear? Is it going to keep following this pattern all the way to 2050? Are we even going to have electricity still in 2050? We don't know that kind of stuff. So I would be very, very careful with making any kind of predictions much outside of what we're looking at, because there's so many things that can change this. Even 2020, what's a better descriptor of unpredictable than 2020? Were they actually selling this many cars? I don't know. I don't have that data. But that, based on the data we had, that's what would be predicted for 2020. So this is the type of thing that you're doing today. You're making scatter plots. You're interpreting them, looking at the association. Is it positive, negative, or none? Same thing with correlation. Positive, negative, or none. And that just means also, is it linear? And then finding lines of best fit or trend lines. Graph it carefully. Draw your trend line so that it's about even. It's about a good predictor. Choose 2 points on the line to make a line of to make the equation of the line of best fit, and then answer any questions that might come from that. And so we'll continue this topic next time, but until then, I'll see you in class. And keep working problems, keep asking questions, and as always, happy mathing.